Hello, everyone. Um, our last class was on orbital diagrams. Today is the follow-up lesson on electron configuration. So today what you're going to learn how to do is how to write electron configurations for those diagrams you've drawn, or even without having drawn a diagram. So first, to refresh our memory with this think and answer, I'd like us to draw orbital diagrams for the following atoms. Again, first thing you do, find this element on the periodic table. So lithium. Let's find lithium. Looks like lithium is right over here, right? So atomic number 3. 3 protons, 3 electrons. Orbitals first, right? And each orbital can take 2 electrons and they must be in opposite spins. Okay, so I put 2 in there. I have 1 more left. So the next highest orbital in energy will be 2s. Right? In this type of diagram, it's fairly simple to know which is the next level up because it's already drawn for you in increasing energy, right? With energy as your y-axis. All right, so next we're going to do the same thing for potassium. Potassium is K, and we see that right over here. All right, so that's atomic number 19. That's 19 electrons. So we start from the bottom. Fill up 1s before moving up. 2s and 2p. If you remember, it's single, 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 and then you double it up, right? That's the empty bus seat rule. You don't double up if there's an empty orbital with the same energy. And all 3 of these 2p orbitals have the same energy. They're considered degenerate. That's what that means, to have same energy. So that's 10 electrons so far. I need 9 more. So let's put 2 and 3s. All right, 7 more to go. 1, 2, 3, 4, 5, 6. So that is 18. I need to put down 1 more. So I put that in 3D? I just completed 3P. Do I put that in 3D or do I put that in 4S? Remember, the rule is whatever is lower in energy. And as we can see by the y-axis here, 4S is a little bit lower in energy than 3D. So that last electron will go into 4S. Let's see. Okay, so we reviewed this already. So here, one of the reasons we need electron configurations is so that we can figure out exactly how many electrons are in the outermost energy level. When an element reacts, it's the electrons on the outermost level that are reacting, that are bonding with something else, that are being taken away from something else, or that are involved in a chemical reaction. So those electrons are known as valence electrons, and the number of valence electrons will determine what that atom can bond with and how many bonds it can make. And so what kind of molecules will be made from it. What is electron configuration? It looks basically like this down here. Right? I'll show you some examples in a second of how that works. So here, if you look at this small portion of electron configuration, this is basically the address for all the electrons in an atom. What orbitals are they in? What energy levels? How many are there? Right? So this big number over here is the energy level, followed by the sublevel, and the superscript is how many electrons are in that sublevel. So if we're to go back to our earlier examples and write the configurations for this, you'd write it as, first you'd write 1s, because 1s is occupied, and there's 2 electrons in it, so you'd write 1s2. The next orbital that's occupied is 2s. That has 1 electron in it, so it's going to be 2s1. Right? So now I have the location for 3 different electrons, and I'm writing what energy level, what sublevel are they in. So let's do the same thing for potassium. 1s2, and this time in 2s, there's also 2 because it's full. And you'll notice that the s sublevel is always filled by 2 electrons. P is filled by 6. P can take a maximum of 6. and then 3s again, that's 2. Forgive my handwriting. 3p it's maxed out with 6, and the 4s is not maxed out, it only has 1. So we just write 1. All right, so this is the full electron configuration for potassium. Which you'll see right here. Okay, so on the IB exams, right, there are questions that will ask you for orbital diagrams, which look like this. You'll have boxes representing orbitals, arrows representing the electrons in those orbitals. Right, so this is the orbital diagram for oxygen. But you might also be asked for an electron configuration, which requires the same exact knowledge from you, but you just have to answer the question a little bit differently. Right? So instead of drawing out boxes and arrows, you're writing the configuration, you're writing the orbitals, you're writing how many electrons go in there. So same concepts, but two different ways of answering it. So let me take you back to the first question. So you'll see in your think and answer, I provided you with information on the order of the sublevels, right? You see visually, you can see that 1s is followed by 2s, 2p, 3s, 3p, 4s, 3d, 4p. So there's a pattern there, but that pattern is broken where 4s comes before 3d. Eventually, you may just remember that on your own, but in the meantime, there is a useful trick for remembering what the order is. So the trick is called the diagonal rule, right? First, you write down the energy levels starting from the bottom. So 1, 2, 3, 4. And then you write in the orbitals. In the first energy level, there's just 1. It's 1s. In the second energy level, there are 2 sublevels, 2s, 2p. In the third, you could guess there's 3 sublevels, 3s, 3p, 3d. And in the fourth, not a surprise, 4 sublevels, 4s, 4p, 4d, 4f. So you have this written out. There's no rocket science there. Next, you draw diagonal lines from the bottom left to the top right. As you draw those lines, it's going to tell you the order of sublevels. And you just follow that order when you do electron configuration. So the first is 1s, then 2s, 2p, 3s, 3p, 4s, and then here's that weird switcheroo. After 4s is 3d, and then 4p. And I'm not 100% sure what's happening in this meme, but I still enjoy it. I think it's 3D showed up and ate 4s is salad and is a cat. And here, 4s just getting in the way. 3D wants to be. Alright, so we're going to use the diagonal rule to help us write the electron configuration for these following elements. Right, so first things first, find it on the periodic table. Okay, neon. Neon is a noble gas. Noble gases are all over here. These are all gases that don't react. So neon, atomic number 10, has 10 electrons. Let's write it in. Oops. Okay. So 1s, 2, fill it up. 2s, 2. Right, you guys see the pattern here? After 1s comes 2s and then 2p. Since neon needed 10 electrons, we're just going to make sure we put a location for all the electrons, right? So 4, good to go, 6 more, and we'll just put in P. That's it. Let's look at argon. Argon is another noble gas right over here, 18. All right, so 1s, fill it up, 2s, put in 2, 2p, that's full 2. right? And that's 10 and 8 more to go. So after 2p is 3s. 3s2. How many more do I have? 6 more, right? Because we need 18. So here's 10, 12, 6 more. So after 3s is 3p. I'll put that in. And you might notice all the noble gases have 6 electrons in the p orbital, p sublevel. All right, next, silicon. Si, right? Silicon is Si. S is sulfur. So 14. Let's come back here. Let's just put that down so I don't forget. All right, 1s2. And if it helps with counting, you might notice that 2p6, once you feel that, that's 10, right? So if you have more than 10, you can just automatically go to 2p6, and you know you have 10 down. Now I have 4 left to go, so after 2p6 is 3s. Put 2 in there, and 2 more left. I'll put those in 3p. And that's that. Okay, so now here is a little trick. In addition to the diagonal rule trick, that might help you. So some of you might prefer the diagonal rule trick. Some of you might prefer this. So one thing I want to point out is the periodic table is blocked, can be blocked off into the S block, P block, D block, and F block. So if you remember, the S sublevel can fit 2 electrons. And let's see how many columns, how many groups are in the S block. Exactly 2. Okay, P sublevel can fit 6. And in here we have 1, 2, 3, 4, 5, 6 families in the P sublevel. D sublevel can fit 10 electrons, and look, there's 10 families in here, right? F sublevel fits 14, and there's 14 families. So it matches up perfectly to help you write out an electron configuration. So what you do is, knowing which areas of the periodic table belong to which sublevel, instead of writing out the diagonal rule, you can kind of take a walk through the periodic table, listing off which orbitals you're going through and filling them up as you go until you get to the element you're looking for. That sounds more confusing, but it's easier to do in practice. So let's give that a shot. So let's come here. Say, for example, we're doing magnesium, right? So instead of writing out the diagonal rule, I know that whatever orbitals are on the inside for magnesium, they're going to be full before I get to that last orbital, right? Because there's no way I'd be putting electrons in the last orbital unless all the orbitals preceding it are full. So as I walk through here, I'm going to be walking through these blocks, and I'm going to list the blocks and fill them with electrons, and I'm just going to keep going until I hit magnesium. So with magnesium, which is over here, I would write, as I'm going through 1s, I'd write 1s, right? This writing is disappearing, so ignore that. So it'd be 1s2, and then 2s2, right? 2 electrons are going in there. 2p6, and 3s2, and I'm at magnesium, and that's my whole electron configuration. Say I was doing silicon, or let's just do the ones we did earlier. All right, we did neon. So how do you get to neon? You have to walk through the S block, fill it up, 1s2, 2s2, this is 2p6, right? You get to the end of the p block at 6, and that's your whole electron configuration. If you're getting to argon, instead of stopping at 2p6, you'd say 3s2, 3p6. So if you found that to be confusing, pretend we never did that, okay? But you might come back to me next year and say that when I try to review this with you, you might ask me why I never taught it to you this way in the first place. But what happens most of the time is the first time someone sees me trying to do this way, it's like frustrating. And then the second time they see a year later, they wonder why I didn't teach him that in the first place because it is actually much easier to do than the diagonal rule once you get it, once it clicks. One other thing I'd like to point out, so the S block, right? It starts with 1s, then 2s, 3s, 4s, right? It matches with the period number. 2p, the p block, there is no p block in the first period. It starts from 2p, 3p, 4p, 5p, 6p. If you guys remember, there's no D sublevel until you get to the third energy level. So even though D looks like it's on the fourth family and fourth period, you actually start with 3D. So say you were trying to get, let's see, chromium. Chromium is right over here. Right over here. If you're trying to get to chromium, it'd be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d4. Right, so the d's are always one number lower than the s's, but then you come right back up for the p's. Okay, let's see. So you also can look at electron configuration for an element and know some things about it. From the configuration, you can figure out where it is on the periodic table, right? If it ends in 4s, it's somewhere here. If it ends in 4p, it's somewhere here. If it ends in 2p, it's somewhere here, right? 5s is on the fifth period. The D block, you have to subtract a little bit. So the D block, if you're looking at 4D, you have to look at the fifth period. But that's a pattern that you'll eventually, it'll become more, it'll come to you easier. Right, and the column, you can figure out what column something is in based on how many electrons there are in that orbital. So if there's one electron, if it ends with a one electron in the s sublevel, it's in here. If it ends in two electrons in the sublevel, it's over here. One electron in p, two in p, three in p, 4, 5, 6 in p, ends here. If it ends in d, and there's one electron, that's here. Two electrons, that's here. So you can kind of gather the location of the element based on that. Okay, so let's write the electron configuration for the following elements using that same thought process. All right, so sulfur. Let's see. Sulfur is over here. So it's going to be 1s, 2, 2s, 2, 2p, fill it up to 6. So let's write that down. 1s, fill it up. 2s, fill it up. 2p, fill it up with 6. And then after that is 3s, 2, and then 3p, 4. And why was it 3p4? I'll show you in a second. Because this over here, aluminum would be 3p1, silicon would end in 3p2, phosphorus would end in 3p3, and sulfur ends in 3p4. So that's the pattern, right? If we did chlorine, that would end in 3p5, because that's one more electron to put in there. Argon, there's another electron, so it would be 3p6. So hydrogen is 1s1, right? It's in the first period, and it's in the s block, and there's one electron in it. So it's the first column of the s block. So, so just to demonstrate a little bit what the connection between orbitals and energy level. So hydrogen, right? Atomic number 1. This represents the nucleus over here. It's going to require one orbital for its electron, right? The 1s orbital. This is what the 1s orbital looks like, and that one electron goes there. Helium, atomic number 2, has a second electron. You don't need another orbital for it because there's space in 1s, so that will go right in there. Now, lithium, atomic number 3, that's another electron. There's no space in 1s, right? So you're going to need 2s, which is a bigger orbital that takes up more space than 1s, so its electron will go there. Beryllium, fourth electron, goes into 2s, right? You don't need another orbital. The next atom needs another orbital, right? After 2s is 2p. So one goes into the first orbital. So that 2p is the sublevel in there. There's 3 orbitals. First electron goes in there, second electron goes into the next orbital, third one goes into the next orbital, and then you see it double up in the second orbital, and double up again, and now you have a full p sublevel for neon. And when you have sublevels that are full like this, that's very stable. They're happy how they are, they don't want to change. And basically all of the gases in this last family, they have full p sublevels and they're happy how they are. They're very stable, right? So when you enter the 3p orbitals, it's just a bigger version of 2p. When you enter 3s, that's just a bigger version of 2s. Right, so looking at these electron configurations, you should be able to see what element it is. So 2p1, right? This is 2p1. So second energy level, p block, first column in there. So let's see. Second energy level, p block, first column. That's boron. All right, number 12. This ends in 2p4. Okay. Second energy level, p block, fourth column. Second energy level, p block, 1, 2, 3, 4. That's oxygen. Third energy level, S block, second column. Third, S, 1, 2, magnesium. Third, 3s, first column. Sodium. 3d10, right? This first row in the D block, that's 3d, and 10 is the last, because D sublevel can only fit 10, so I don't need a count, I just know it's the last one, so that's zinc. Let's ignore that. And here, let's make this the last one. 4p, fifth one, right? So 1, 2, 3, 4, p, and this bromine is the fifth one. Krypton is number 6, right? This last column is always the 6th electron in the p block. All right, let's keep on moving. Okay, so you might have noticed back here, some of these electron configurations get very long, right? That's tedious, it's annoying to write. So there is a shorthand notation. It's a way of abbreviating long electron configurations. So since the most important electrons are the valence electrons on the outside, we can skip the parts that we know are full, and then finish the configuration. So how do we do that? We take this longhand configuration, right? We look at the valence electrons. We're going to make sure to write those. And then we see the core electrons, right? Core meaning on the inside, valence meaning on the outside. These core electrons match the electron configuration for another element. So instead of writing all of this out, we see what that other element is, and we just write that in brackets instead. So 2, 4, 10, that's 10 electrons, right? What had 10 electrons? Neon. So this over here in green is the electron configuration for neon. So instead of writing this whole thing out, we'll just write an E in brackets and use that to finish writing the electron configuration for chlorine. Because after neon, what do we have to do to get to chlorine? After neon, we have to go through 3s2 and then 3p5. right? So we write Ne, 3s2, 3p5. So you get the gist here. So the method is whatever element you're writing shorthand configuration for, find the symbol for the noble gas that precedes that element in brackets, and then continue writing the electron configuration from that point. So here you've got germanium, right? So let's find that on the actual periodic table. It's right here. So we're going to go one up. We're going to go one up and then all the way over. What is the noble gas over there? It's argon, right? So our starting point is gonna be argon. If we were using something like silicon, you would go one up all the way over, you'd use neon, right? If you were doing fluorine, you'd go one up all the way over and you'd use helium. But we're using germanium, so one up all the way over is argon. Right, so you just write AR in brackets, and all of this, the electron configuration for all of this, you don't have to write anymore, right? That's assumed in here. If the AR is there in brackets, it's implied what the electron configuration is that you just skipped. And then you just write the rest, right? You just have to get from here to here, to germanium. So to do that, next comes 4s2, right? Because you're in 4s, you're gonna max it out at 2, and then after 4s is always 3d. Max it out at 10. How many more electrons do you need to get to germanium? 1, 2, and it's in the p block. So 4p2, right? So this is shorthand configuration. You just go up from whatever you're looking at all the way over to the noble gas, write that in brackets like we did here, and then write out the rest. Right, so this is the full electron configuration for chlorine, which is very long. So instead of writing this, you write it as that instead. Shorter, neater. The outer ones stays the same. Right? Those are the ones that are going to interact in chemical reactions anyway. Those are the ones that matter. And those outer ones are on the third energy level. Okay, so let's do a little bit of practice with shorthand configuration. So from the shorthand configuration, you can still find out what the element is, right? So 4s2, fourth energy level, S block, second family, so calcium. Vanadium, right? We're going to write the shorthand notation. So vanadium is having some trouble finding it. It's somewhere. Here, okay. So vanadium, right? It's in the fourth period. So we just go up to 3 and go all the way over and we see that's argon, right? So we're going to write AR. And after argon, to get to vanadium, we have to go through 4s2 and then 3d, 1, 2, 3. So 4s2, 3d, 3. All right, here, whatever this is, let's figure out 2p5. So we're going to look in the p block, second row, fifth family, 1, 2, 3, 4, 5. That's fluorine. So I think you get the gist of how to do this probably. So let's skip through. All right. You can try it yourself and check your answers. Okay, so one last concept to add. So things are happy when they're stable. When they're stable, they stay how they are and don't change. right? Things that aren't stable, they will change to become stable. If I have a coin balanced on edge, it's unstable, right? It will fall flat to its side so it can become stable. If I have a coin flat on its side, it's not going to unflip itself and stand up on edge by itself, right? So in atoms, full energy levels are particularly stable, right? If S has 2 electrons in it, it's happy. P likes to have 6 in it. D likes to have 10. F likes to have 14. If they have that, they don't want to change. They don't want to gain electrons. They don't want to lose electrons. Um, they're also almost as stable if they have half full electrons. So S, if it has 1 electron, it's pretty happy. P, 3 electrons is pretty stable. D, 5 electrons is pretty stable. F, 7 electrons is pretty stable, right? So those two things are fairly stable. So full energy level is very stable. Half full sublevel is also stable. So what does this mean? How does this affect you? Unfortunately, it creates weird exceptions to some rules that I just taught you. So anything that's blocked off right now, those elements have a half full. Like the standard configuration you would write out would lead to them having a half full orbital, right? Everything over here would have 5 electrons in the D block. Here, 3 electrons in P block. Here, 7 electrons in F block. They don't really want to change much. So what exceptions exist? Chromium and copper. Why? If you write out the electron configuration, you'll see that 4s has 2 electrons and 3d has 4 electrons. However, that's been found to not be the case. In reality, 4s has 1 electron and 3d has 5. Why? Because chromium gains stability when this D sublevel is half full. So what does it do? This D sublevel, instead of just being happy with 4, will take one of these from S, and it'll end up with 5, and 4s will be left with 1. Chromium is a similar situation. If you write out the electron configuration the way I taught you, there will be 2 electrons in 4s and 9 in 3d. However, what you find is 3d, instead of having 9, actually takes 1 from 4s and ends up with 10. Right? So chromium gains stability because it ends up with a full G sublevel. Sorry, copper. So half full sublevels are relatively stable because it minimizes electrostatic repulsion among the electrons. Electrostatic repulsion is basically the repulsion between two negatively charged particles, right? They push each other away, or also theoretically two positively charged particles. But since we're talking about electrons, if you have 5 orbitals and each of those only have 1 electron in them, they're stable, right? Because they're not being pushed into proximity. Another point to make is the 4s and 3d sublevels. So the 4s and 3d sublevels, you can see, are fairly close in energy, right? There's a big gap between 1s, 2s, 2s and 2p, all of these. But 4s and 3d are very similar in energy. So what that means is it doesn't take much for an electron to go from this 4s energy level, from this 4s sublevel to 3d. So it doesn't take much energy to move, and once you've moved, you have half full sublevels, and you also don't have doubling up in 4s anymore, so electrostatic repulsion is minimized, right? Those are the factors that push for this to happen. So it's actually more stable for these electrons. Instead of staying together in 4s and having 4s be complete, it's more stable for it to go over here and fill that last orbital in 3d. And the IB loves exceptions. So chromium and copper will always come up, right? So the way you remember that is chromium has 3s2. Was it 3s2? No, 4s2, 3d4. 3d4 is just one away from being half full. So it snatches it from 4s and becomes 3d10. I mean 5. Similar story with copper. Copper is 4s2, 3d9. 3d9 is that's 3d is one electron away from being completely full, which is very stable. So it snatches one and takes it away. Right now you have a full 3d sublevel and a half full 4s. Oh, all right, there's one more thing to teach you. Okay, so electron configuration for ions. So two things to remember. For anions, meaning negative ions, when you add electrons, they go to the lowest available empty orbital, right? You already know how to do that. Cations, however, are a little tricky. You remove electrons not from the last orbital that you wrote down, but from the highest energy level. So let's show you what I mean. No. So here, so aluminum has this configuration, right? So aluminum plus, the first electron that's taken away, because aluminum plus means it's lost one electron, will be this one. It's the highest energy level, highest energy orbital. Get rid of that. Aluminum 2 plus, one of these 3s electrons will be taken away. Aluminum 3 plus, the second 3s electron will be taken away, and you'll just be left with this. Where it gets tricky is with transition metals. Transition metals are these metals in the middle, right? That's just the name for them. In the D block, those are called transition metals. So why does that get tricky? Because in transition metals, 4s is written before 3d. And what I said earlier was that electrons, for cations, electrons are lost from the highest energy level, right? So if we look here, 4s is written, 4s is written before 3d, right? So you might think the electron from 3d is being taken away. However, 4 is a higher energy level, and it's actually taken away from 4s. So for practice, right? Iron has 26 electrons. This is the configuration over here. If we lose some electrons, if we lose 3 electrons, the first one is going to go from here. Why? That's because that's the highest energy level. The second one will also go from here. But then if you have to lose a third one, right, after this has been cleared out, that will be taken from here. So what that means is whenever you remove an electron, find the highest number energy level, take it from there first. All right, that is the end of today. All right, see you all next time.